Hi, we are data analysts from Sony Corporation. Today we are going to present our analysis result based on the Youbike rental dataset. In daily Youbike service, users rent a bike on the station and then return it on another station. But sometimes there are too many bikes in some stations, so user can't return the bike at once. Otherwise, sometimes there's no bikes. As a result, people can't rent bike right away. This situation decrease usage efficiency and also lower the service quality. People may be less confident in government Youbike service. To meet the demand of users, government has to construct an effective plan to optimize the dispatching routes. Here is our agenda. We start from the business problem, then go through the data and do some basic visualization. In model part, we adopt two kinds of model to solve problems. First one is multi-level model. Second one, we use Gaussian process model. And eventually, we make conclusions according to our model and analytical result. Bike dispatching is always a problem for Youbike company. There will be excess supplies or demands in some rental spots that need tackling with. In the following analytic, we focus on the bike dispatching problem. We strive to find user usage habit or pattern to help we know each bike station rental situation. In this project, our goal is to estimate rent and return counts of each station by hour. In order to optimize the dispatching route, we achieve this goal by two steps. First, we try to find user usage pattern from the data and collect variable feature data that might affect whether people rent Youbike as a way to move in the city. Then use the technique of multi-level modeling as well as Gaussian process to build model that can effectively predict future behavior. And second part is data overview and visualization. The bike rental dataset we use is within January of 2016. Here are some features below. There are totally 217 bike stations are in service. The dataset also includes usage date, duration of that journey, cost of that journey, rent and return stations, area for the Youbike station, and station name. Here are the top 5 popular stations. In these two tables, we can see most of the users are in Da'an and Xinyi district. The first place is MRT Gongguan Station. In January, there are totally about 23,000 usage counts. From the table, we know these popular bike stations have similar usage counts in rent and return. We want to know which station is short of bikes and which station has too many bikes. So we calculate the netting number for each station. We use number of return minus number of rent to get netting number. If netting is positive means the station has excessive bikes. If netting is negative means we need to supply more bikes for this station. From table we can see Taipei Medical University has too many bikes, while MRT Zhishan Station needs more bikes for people to use. Here we use heat map to analyze the relation between hour and data and area. The horizontal axis means area and vertical axis is hour. The dark area in the map means there are more rent or return users in this area at this hour. We can see Da'an, Xinyi, and Zhongzheng districts have more users than other areas in these two maps. And look at our part. We can see most of users are using bikes at 8 to 9 o'clock and 12 to 19 o'clock. And in this heat map, color means the netting number. Dark area means this station has excess bikes. Light area means shortage. It needs more bikes to meet the demand of users. And we can see Wanhua district has excessive bikes at 5 to 7 p.m. However, Wanhua district is short of bikes at 7 to 8 in the morning, and Zhongzheng district is also short of bikes at 4 to 5 p.m. Then we change the horizontal axis from district to weekday to see relation between weekday and hour. We can see evening is darker than afternoon period, especially in the weekend. It may infer that most people rent bikes in the afternoon and then return bikes in the evening. And next part is data visualization.
So the first thing to do before using GGMap is that we have to get every station's latitude and longitude. Because GGMap uses latitude and longitude to plot on the Google Map, so we have to find out these coordinates through one of the GGMap function called geocode. If you just put the range station name from the raw data, there's a very high chance that the geocode function will get the wrong coordinate that is outside of Taiwan, maybe some other country. So in order to get the correct coordinate, I use a small trick. I just add Taiwan Taipei before each station name, and the result is much better. Now we have the latitude and longitude of Taiwan Taipei. We can plot with GGMap. We plot majorly on this attribute of the raw data, like use time or rent number of bikes. So we plot them by station. So this plot means every station's total use time of January 1620, and we can see most of the heavy use is around Datong and Zhongshan district. Yeah. Maybe we can make good deployment of Youbikes, like based on these statistics. And the next is the number of use of Youbike, and it turns out that in this plot, Da'an district has the most bike use. So maybe we can focus heavily on Da'an district based on this plot. Yeah. And this is the result if we plot Youbike net flow by every day. We can see that it seems some days have huge net inflows, that is red dots, and huge net outflows, blue dots on some stations on some days. And we can see most red dots appear on Da'an district, and most blue dots appear on Zhongshan district. So maybe we can just move some bikes from Da'an district to Zhongshan district on some days based on some this knowledge. Yeah, and this is my part of visualization. And the next is we plot each raw data on when we use the route of every station to every station, and this is the result. We can see that it stacks. That means if a route is heavily used, we can see more permanent route. Like we can see almost all is on around Da'an district or Zhongshan district based on this plot, and this is the result. Yeah. Okay, so next part is about multi-level models.
Here we go to the model building part. We can see in previous beautiful animation, most of the net ins are 0, so which have dropped out too many information. So we are not going to use that as our target. The target we are going to use is a rent count for every station, which is more explicit than the net flow. We think rain is the key factor of the renting volume. So first we crowd the perception data of the Taipei city in the scale of every hour. But afterward, we want more detailed information for every station. So we made a crowder for renting data by district. That takes a lot of time. And we can see at the right bottom, the x-axis is the rent data for Taipei city, and the y-axis is rent data by district. So we can see the rent is not uniform in Taipei. in Taipei City. Okay. For data processing, we downsample the scale renting and returning to hourly data. And we also calculate the pair relationship between stations. For model building, Youbike renting is happening randomly, so we think it should subject to a Poisson distribution. At the very beginning, we tried some naive linear models with our dummy and perception, and add on some interaction between them. We tested by information criteria WAIC, and see the interaction model works, but multi-level model make no difference. As we look closer to the graph at the right one, we can see that we underestimate when there is no rain, but we overestimate when it rains. That is caused by the nonlinearity rain effect. So we could use the older data taught by Sunny to scale the rain effect, or we can simply use the log function as a cure. Log is sharp at the start and flat at the end, just like the rain effect, which is obvious. Which is obvious when it's near zero and is not that obvious when it's rained a lot. Okay. Also, rain does affect. Okay. And so our log and accumulated rain works magic. It improves a lot in the WAIC, the information criteria. Okay. But okay, so this is another plot to show how good we are modeling these things. And well, you see the model fits the truth data. The green one is the prediction, and the red one is the truth. And we can see it fits very well. And the same model also fits in another station too. However, when we test by the unseen time, so we train with our 1 to 500 and test with 500 to 744, we can see the prediction is not really good. And we look closer to the graph, we can see there are some extreme value between hours, especially when there's rain. And we think that is because the rain effect does not happens on every hour in our training data. And so we think of two main solutions. First is about there must be some correlation between the beta of hour and the beta of hour and rain interaction. Second resolution would be we can use a regularization method. So we put a small prior on that, and we can see the effect. However, when we test it by unseen station, it's not working very well either. So we are quite depressed. So where's the hope now? To sum up, here's are the challenges. First, we have no clue of predicting holiday. Like we have a peak, we have a spike at the January 1st midnight spike. So we don't have that much information. We have already used up all our features. And second, we have we don't know how to make cross-station prediction, and we don't know how to make future prediction. So we have to achieve the adaptive predictions. Maybe we should predefine correlation between stations, like by pair counts or by geological information. And second, we can put more dummy variables like some geological information. And the last one, Oh, and the third one, maybe we can put more labels in the multi-level model and make a complicated model. Or the last one, we can use time series. Some events are not included in our feature, so time series may help. So next part, we'll go to the time series model.
Okay, so before talking about the Gaussian process models, I would like to spend a little time going back to the data and explain why we choose Gaussian process as our model. After data preprocessing, as mentioned before, there is the hourly rent and return count of bikes in January 2016. And it is easy to see these data have both a non-stationary mean and a non-stationary variance. There is also a clear periodic component to this data, as you can see from the graph. So this is the reason why I'm going to use Gaussian process to perform a time series prediction. And know that I will use the data of a station for model training and testing to avoid the time-consuming problems. Okay, so as the data is prepared, the next important thing is to define the kernel of Gaussian process. So as you can see from the slide, I'm going to use two kernels in this case. And let's take a look about the kernel. The first kernel is the basic one, which is called the square exponential covariance function, also known as RBF in machine learning. And the sigma here is the estimated variance accounted for by the function k, and rho is a length scale parameter that governs the decay rate. So the smaller estimated values for rho indicate a faster decay rate in the covariance between 2 points as a function of time. And the second kernel is to add a covariance function that incorporates the periodicity. Okay, so the last step is to just sum them up as our final kernel. Okay, so let's start to train our model. So my first strategy is just to use the simple time series to see how Gaussian process can fit the data. And I trained the two models for two stations separately, which is station ID 45 and 132. And I predict the rank counts for test data using the last week rank counts of 7 weeks of our in training data. It sounds like a very simple and stupid strategy, but I just want to show how Gaussian process can fit the data. So as you can see from the result, the Gaussian process still perfectly fits the data. The RMSE score is quite low compared to the test data. Yeah, you can see there's a huge gap. And I just want to show you this funny result. But as you can see, the series overfitting problems and the bad predictive power of the model. But I think it would be good to use this result as the model baseline. Okay, so to improve the model, the next strategy I'm going to do is to add an important derived variables and convert the current input feature. I'm going to convert the time point to our sequence number by week. So each week I get a 168 sequence of hour, and each hour sequence number is paired with its hourly rank count. And next, I'm going to use the first 3 weeks to train the model and leave the last week for testing. Okay, so here's the result. It seems quite better compared to the baseline. We lightly solve the overfitting problems and also improve the test scores, which is a good thing. Although you may argue that the RMSE is still bad, but I think it's a good process so far for improving the model of time series forecasting using Gaussian process if we want to keep improving this model in the future. So here I list some recommendations for improving the models, and I want to talk about the two parts. The first part is for time series, and the second part is for Gaussian process. So to improve the time series, the first thing I think we should try using multivariate time series to train the model. Since time series with a single value in a period may lose some important information, such as the RAM feature. And the second thing is to consider more on time series effect. For example, we can derive some time lag variables and add into our models. And the third point is we should get more data to capture the trend effect of the time series. I think it would be better to our models. And the second part is for Gaussian process. I think we should keep fine-tuning hyperparameters of the kernels, since the kernel to the Gaussian process is really play an important part for training a model. So I think it was a key point if we want to keep improving. And the second thing is just try other non-Gaussian distribution to train the model. For instance, we can use a Poisson distribution. And the last point is, I think we can add a white noise to the model and to capture more uncertainty.
Now let's end with some takeaways from all the hard work we've done. First, there are certain patterns with regard to the trend of the bike's net inflow. As the plot shows, Da-An and Zhongzhen have above average rain count, and 8 a.m. and 9 a.m. in the morning also have high rain count as well. Being able to predict the number of inflow can help Youbike company form better dispatching plan. More practically, if Youbike company can predict when and where will lack Youbikes and when and where they will have excess supply of bikes, they can optimize the dispatching plan. Then, with the help of multi-level models, we can get a smaller wake, which means the model is closer to the unknown true data generating process. We know that models are flexible and objective, as long as we can figure out how to improve the model, either by adding new predictor or by changing the type of distribution, such as changing a normal distribution to Poisson distribution, we can do better at predicting. Time series method turns out to greatly improve the performance of the model. Yet, there is still plenty of rooms for improvement. Model-wise, how can we do better? Here we list some of potential ways to do better. First, we can improve our model using distance between stops as a covariance matrix. This matrix can be used as a predictor for the model. By building correlation between each category, the model may perform better. At least it's worth a try. Second, the nature for each station serves as an important predictor that we might have neglected in the model mentioned before. For example, whether or not a station is near busy bus stations, or whether or not the station is in a residential area, can greatly impact the pattern of the net inflow. Lastly, adding white noise or time lag variables, as mentioned before, may also work magic. It's our honor to help your company to analyze this issue. Thank you for listening.